Solana is a blockchain protocol that was created with the goal of achieving high throughput and low latency while maintaining security and decentralization. Its white paper, titled A New Architecture for a High-Performance Blockchain, introduces a set of design principles and mechanisms that together aim to solve the scalability limitations of earlier blockchain systems. The fundamental problem identified is that blockchains such as Bitcoin and Ethereum struggle with trade-offs between speed, decentralization, and security. They either sacrifice transaction throughput in order to keep the system decentralized and secure, or they risk centralization if they attempt to scale up performance. Solana's proposal is to create a system that can handle tens of thousands of transactions per second with sub-second confirmation times without losing the trustless and permissionless qualities that define blockchain technology. At the heart of Solana's design is the concept called proof of history, abbreviated POH. Proof of history is not itself a consensus mechanism but rather a cryptographic source of time. It functions as a verifiable delay function, producing a sequence of hashes in such a way that each new hash depends on the previous one and cannot be computed without completing all prior steps in the sequence. This creates a historical record that proves the passage of time between events. When transactions or events are fed into this stream, they are automatically timestamped and ordered. This allows the network to agree on the order of transactions without requiring each node to communicate constantly about timing or sequence. In other words, proof of history provides a built-in clock for the network. This clock enables other parts of the system to run more efficiently. Solana combines POH with proof of stake, where validators put up collateral in the form of SOL tokens in order to participate in consensus. Validators propose and vote on blocks, but because proof of history provides a trusted sequence of time, they need to exchange far fewer messages to agree on the order of transactions. This greatly reduces communication overhead and allows consensus to be reached much faster. Solana's consensus algorithm is called Tower BFT, which is an optimized version of Byzantine fault tolerance that uses proof of history as a clock. Tower BFT reduces the latency and messaging requirements of traditional BFT protocols by anchoring votes in the verifiable history. Beyond consensus, the white paper describes several other innovations that allow Solana to scale. Sealevel is Solana's system for executing smart contracts and transactions in parallel. Rather than processing one transaction at a time, Sealevel analyzes which transactions do not conflict with each other and can safely run simultaneously, allowing the blockchain to make full use of modern multi-core processors and GPUs. Turbine is Solana's block propagation protocol. Instead of sending entire blocks to all nodes at once, it breaks them into smaller packets and distributes them through a tree-like network, greatly reducing the bandwidth required from any single node and ensuring faster distribution of data across the network. Pipelining is another component, where the process of transaction validation, signature verification, and writing to the ledger are split into stages that can run concurrently, much like an assembly line, allowing different hardware units to work on different parts of the process at the same time. These techniques combined are designed to maximize throughput and minimize latency. The white paper sets ambitious performance goals. It envisions a blockchain that can reach tens or even hundreds of thousands of transactions per second with confirmation times measured in fractions of a second. This would allow blockchains to operate at what the Solana team calls web scale, competing with traditional centralized payment processes and internet services. Achieving this requires assuming a modern hardware environment, with fast processors, significant memory, and high bandwidth connections between nodes. The system is designed to take advantage of the continual improvement in hardware that follows Moore's law, expecting that as computers and networks get faster, the Solana blockchain can scale up accordingly. Every system involves trade-offs and limitations, and the Solana white paper acknowledges several. Because of its reliance on high-performance hardware and fast networking, the barrier to entry for validators is higher than in some other blockchains. This can raise the risk of centralization, since fewer individuals or organizations may have the resources to participate as validators. Additionally, while proof of history reduces coordination overhead, it introduces complexity and requires careful implementation to avoid bugs or vulnerabilities. The need for continuous hashing at very high speed also means that Solana nodes consume significant computing power, even if not in the same way as proof-of-work systems. The overall complexity of combining proof of history, Tower BFT, Turbine, Sealevel, and pipelining means that there are many moving parts that must function correctly together for the network to remain stable and secure. Nevertheless, the design offers important advantages compared to other blockchain approaches. Unlike Bitcoin, Solana does not rely on energy-intensive mining. Unlike simpler proof-of-stake systems, it has a built-in clock to order transactions, which reduces delays and messaging requirements. And unlike many earlier smart contract platforms, it supports parallel execution of contracts, making full use of modern hardware to process large numbers of transactions simultaneously. This combination allows Solana to position itself as a high-performance, general-purpose blockchain capable of supporting decentralized finance, NFTs, real-time applications, and other use cases that require low cost and rapid confirmation. In practice, Solana has already been used for applications ranging from decentralized exchanges to NFT marketplaces, often chosen because of its speed and low transaction fees. Developers see opportunities in using the network for gaming, streaming, and other applications that demand real-time responsiveness. Critics continue to point out the risks of centralization and occasional network outages, which highlight the challenges of maintaining such an ambitious system at scale. Still, the core ideas laid out in the white paper remain the basis for Solana's ongoing development and adoption. For more insights on Solana, proof of history, and high-performance blockchain architecture, remember to like, subscribe, and keep learning, here at Crypto in Black and White.